Hello everyone, and welcome to today's live broadcast, Economies of Scale in Cannabis, moving from lab scale CO2 supercritical fluid extraction to production scale, presented by Lalit, Chordia, the President and CEO of Thar Energy. I'm Susie Valdez of LabRoots, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I want to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the Ask a Question box located on the far left of your screen. Type your questions into the drop box that appear on that screen, and we'll answer as many questions as we have time for at the end of the presentation. If you have any trouble seeing or hearing this presentation, click on the Help Desk button located on the promotional board at the bottom center of your screen, or use the Ask a Question box to let us know you're having a problem. This presentation is educational and thus offers continuing education credits. Click on the Continuing Education Credits tab located on the top right corner of the presentation window and follow the process to obtain those credits. Please join me now in welcoming Dr. Chordia. I will now turn the presentation over to him. Welcome, sir.
Good afternoon. Thank you for that introduction. I appreciate it. And welcome to all of you. This is Lalit Chordia. I'm the CEO of Thar Process. And today I want to talk about supercritical fluid extraction in particular, but in general, cannabis extraction. We'll start off with a background on Thar and Thar's experience in supercritical, the different extraction techniques that are out there, and we'll follow up with issues related with scale and scale up with supercritical, both on the extraction side and also on the purification side. For those who do not know what supercritical is, you will see a slide on the right-hand side, and at the extreme right, you will see a point which says critical point. As long as you operate above the critical pressure and the critical temperature, you're in the supercritical region. That is what we are working with here. Now, if you look at the horizontal line at the critical point, as long as you're above this point and horizontally, you can decrease the pressure, you can increase the temperature, you can play with all of these parameters to get the right extraction conditions you need for the process you're trying to do. Now, at the very end, I'll summarize with all the lessons that we have learned today. So to give you back the history of supercritical here, in 1982, we started a company called Suprex. We were the first supercritical company in the whole world. So you can see the background. We have been doing this for the last 35 years. In Suprex, we developed instrumentation specifically focused on extraction and chromatography. We launched the first capillary SFC in the world, and ultimately the company was sold to ISCO in 1990. I started Thar in 1990. In 1990, we started working on various equipment for supercritical, but not the analytical side. We made pilot plant and production scale. Onwards, we went on to spin out a number of divisions from Thar, and we started building large-scale systems, and we have built over 20 production scale. I'm talking about 500-liter, 1,000-liter systems in the last 10 years. Between 2007 and 2017, we have done a number of different things. We built a prep scale SFC, onwards to build the largest back column SFC in the world. We built a countercurrent column going up to 30 feet long, where you can do separations. Instead of using a chromatographic separation, we can use a countercurrent separation. Then in 2011, we built a large facility at the back of our building that we are located today. It is a 25,000 GMP facility where we extract astaxanthin, which is a antioxidant from an algae called Haematococcus. And late last year, we doubled that capacity. So right now, we are one of the largest, if not the largest, algae producing company in the world over here. Algae extract, I say, using supercritical fluids. The extraction pressure is fairly large. We're talking about 15,000 pounds of pressure. So it's one of the highest extraction systems in the world. Onwards, we have moved into also making chromatographic separation equipment, which is HPLC and SFC. We do both depending on the sample. And we have built a 600 mm, which is a 24-inch ID column, 3 of them for a pharmaceutical company overseas. So we have a strong background in both extraction and chromatographic separations. The mission of Thar process is to be a global leader in supercritical fluid technology and equipment by providing solutions involving chemistry, design, process, development, and optimization. We take our customers from concept through commercialization. Thar's competitive advantage in this supercritical area, we are the most experienced supercritical only company. We have been doing this for the last 35 years. We didn't start this a few years ago when the medical marijuana or hemp extraction market came into force. We have been doing supercritical long before people thought green technology was fashionable. From a design point of view, we bring all the different process and equipment technologies together. We manufacture our own equipment, so we put things together, which is optimized solutions based on the initial feasibility studies all the way through production. And all systems, as I mentioned earlier, and major components are designed, developed, and assembled and warranted by Thar process. And this is all done out of Pittsburgh, Pennsylvania. Lastly, we are customer-centered partnerships from proof of concept through commercialization for their production solution of choice. So we are very customer-friendly company. So the examples of work that can be done with supercritical is you can do polymer purification, you can remove solvents from synthetic DNA, astaxanthin from algae, you can de-oil lecithins, recovery of residual specialty oils, extraction of spices, flavors, fragrances, and any active ingredient from herbs. In short, if the word oil is used, we can probably extract it from the natural product. Besides extraction, supercritical can be used for reactions, impregnations, coatings. So there's a variety of applications that you can use it for. And if you're trying to make specialty products using these cannabinoids, you can use the impregnation technology to do it for any kind of applications you might have. What I'm going to start off today is talk about different extraction technologies. There are really 5 of them out there. You can do with ice water, which is one of the oldest techniques, where you take your cannabinoids, you take your plant material, grind it up, put it in ice water, and since THC and CBD and all the cannabinoids are heavier, they settle down on the bottom. It's a very simple process, but the overall extraction efficiency is low. You can use hydrocarbon solvents like propane, butane, hexane. These are all non-polar solvents, very similar to supercritical CO2, but the disadvantage of these, they are highly explosive, so you have to have explosion-proof requirements, and there are a lot of regulatory issues on how much you can have these solvents at your building, and constraints associated with that, and there is always a worry of explosion, so you have to be a little careful about this. The other technique, which is the RSO, which is similar to the hydrocarbons, but instead of using propane, butane, and hexane, you're using naphtha or isopropyl alcohol. The process is still very similar. The other extraction solvent, which is becoming popular these days, is ethanol. Ethanol is significantly more polar than CO2, so the kind of compounds, the selectivity is very different. The ethanol is a very good solvent because it is physiologically compatible, But again, from a regulatory point of view, there are restrictions on how much you can use. So if you're trying to scale this, it becomes a regulatory nightmare to handle ethanol on a scale. The last, of course, that we are talking about today is supercritical CO2. And we believe supercritical CO2 is a great solvent. And the question is why? And if you look at the list here, first we start with it's a zero global warming potential. It's a zero ozone depletion potential. It's physiologically compatible. It's inexpensive and available everywhere. We are talking about $150 a ton, which is really inexpensive. And the most important is it does not need any explosion-proof requirements. So you can almost put it up anywhere. The other advantage of supercritical is by varying the temperature and pressure, you can extract different things. And by running a low temperature extraction, you can get high selectivity. But the negative of low temperature extraction is that you have a high solvent to feed ratio. So you have to run the CO2 that you are using for, about a factor of 10 to get the same overall extraction efficiency. On the other hand, you can increase the temperature, so you can do high temperature and high pressure, and you get a very high efficiency of extraction, but the selectivity is low, so you end up extracting things like waxes, which you have to remove further. But overall, the solvent to feed ratio is low, which means you get high productivity. So there is advantages and disadvantages of any of these things that you do. You have to look at the pros and cons and decide what is the right thing for you. Now, in a typical process, you can see the schematic on the left-hand side of the screen. You have a pump where you can pressurize the CO2, and it goes, you preheat it, then it goes into the extraction vessel, you extract it, you depressurize it, and you collect it in a separator, and the CO2 comes out and you recycle it. So the major components here are pumps, vessels, and separators. These are the three major components that govern the scale-up issues. And you can get these vessels all the way down from 1 liter, 5 liter to as much as 500 liters or larger, depending on who you go to. Now, when you come to sizing, the important question you have here is, how do you determine what size you need when you do scale up? The first and foremost question that comes here is, what is the solvent to feed ratio? You do that trials on a lab scale 5-liter system and then determine what's the solvent to feed ratio. The reason this is important is, as I mentioned earlier, temperature and pressure play a major role in the extraction. So if you're doing low temperatures, you may need a solvent to feed ratio of even 120. And if you do high pressure and high temperature, the solvent to feed ratio is 10. So solvent to feed ratio controls your sizing. So that's the first thing you need to know. Once you know solvent to feed ratio, you define what is the capacity you're going for. Is it 10 kilos a day, 100 kilos a day, a ton a day? What is the capacity? And based on the capacity and the solvent to feed ratio, you'll get to a number which is the total amount of CO2 that you need on a daily basis. And the next question becomes, once you have this number, whether you're doing this in an 8-hour time frame or a 24-hour time frame, you can calculate the pump flow rate. So we start with the basic thing here. The pump flow rate defines your capacity. It is not the vessel size, which is what everybody thinks. It is actually the pump flow rate. If you have a small pump and you put a vessel, and if you even double the size of the vessel, it doesn't mean that your capacity has gone up, because the capacity is controlled by what is the flow rate of the pump. So that is the most critical thing from a scale-up point of view, is defining the pump flow rate, which is a function of the solvent to feed ratio and the capacity that you need. Once you define the pump flow rate, then what you do is you design the vessel diameter. And the vessel diameter is defined by the linear velocity of this flow rate inside the vessel. If you have a very large vessel diameter, then you have a very low linear velocity. And if you have a very small vessel diameter, you have a very high linear velocity. If you have a high linear velocity, the herbs or the plant material will go to the other end of the vessel and get stuck, potentially plugging it. So you want to make sure you have an optimum, and there are numbers that we use over here, typically in the range of 20 feet per second. So we use those to calculate what the vessel diameter should be. Once we do the vessel diameter, we define the vessel size by determining the vessel length. And that gives us the total diameter, the total volume of the vessel that we need. Lastly, what I want to mention here is the subcritical CO2 extraction, which has high solvent to feed ratios, will force you to use a vessel which has a very large diameter, which obviously increases the cost because of the pressure. While the supercritical extraction, which is high pressure, high temperature, has much lower solvent to feed ratios. That's how you come up with sizing for a large scale or on a scale up issue. Now I can show you some vessel equipment that are available in the marketplace. The one on the left that you see typically Waters provides 5-liter systems to 10-liter systems. The one in the middle is medium scale. You can get them from Apex. And one on the right is a large scale system. And this is a 750-liter 2-vessel system, so a total of 1,500 liters. This one actually operates at 15,000 pounds of pressure that I talked to you earlier about. And we extract astaxanthin, so this is our system at our facility in Pittsburgh. So you can get variety of sizes, and you need to size them based on the previous slide that I showed and come up with the size that you need. So again, talking about scale-up issues over here, how do you calculate cost? Here's from our experience. We say capital cost is y power x. In other words, if you were to double the size, so y is a factor of 2, and we power it to 0.68, then the capital cost will go up by 1.6. So it's not linear, it's not logarithmic. The power is typically to the power of 0.68. So every time you double the size, you can assume the capital cost goes up by a factor of 1.6. Typically, the utility cost is a function of flow rate, which largely remains the same on a per pound basis when you process it. So you don't get much reduction by going a scale up, maybe about 3% for every doubling of the flow rate. So you don't get a substantial reduction on utility costing. And finally, you come to labor. The unfortunate part of labor is labor remains the same whether you use a 5-liter system or a 100-liter system or a 1,000-liter system. So labor becomes the largest portion of your cost. And as you scale up, labor becomes a smaller portion of the overall cost. So it's very critical for you, if you want to drive the overall cost down, to scale up and scale up to as large a scale as possible. The other way to design your system is to have different configurations. The basic system is you have one vessel and one pump. And that's simple, straightforward. You have a vessel, a pump, and a separator, you're done. That's what most people sell. Now you can go from here and say, how do I increase my capacity? You can have 2 vessels and 1 pump. And while the first one is running, you can load the second vessel, get it ready, and get it moving. And that will give you a 30% increase in capacity. That's a typical number. Sometimes it's a little high, sometimes it's a little low. It all depends on what your total extraction time is. Shorter the extraction time, greater effect it has. longer the extraction time, less effect it has. So you can go from a 1 vessel to a 2 vessel system, and all you're doing is adding a cost of a vessel and couple valves, and that immediately increases your capacity by about 30%. The next thing you can do is a series configuration. This is very interesting. So what you have here is 3 vessels, and 2 of them are connected in series, and you have only 1 pump. So the same pump that you used in the first 2 configurations, you can use in the 3rd one, and this CO2 will go from the first vessel to the 2nd vessel. And because you have 2 vessels in series, you have the highest extraction efficiency. In other words, if the first and the 2nd one gave you a 80% extraction efficiency for the same conditions, you'll definitely get more than 80%. It could be 85, it could be 90. It's a function of the application, but it's the highest you can get. And while the first 2 are running, the 3rd one is being unloaded, cleaned, and loaded back again. So then you switch and you take the 2nd one out, put the 3rd one in front of the first one, and you continue the process, and you continue this every time. So you will be able to get the same 30% as the previous one, but your overall extraction efficiency will be higher, and you'll come out with more material, the material that you're looking for. That's important. And the other option here is you can have 3 vessels and 2 pumps actually, and that will double the flow rate, or you can have 1 pump with 2x the flow rate, and you can get 2.6x, which is the highest extraction configuration from that point of view. The last one is you can do a parallel configuration, which is 2 vessels and 2 pumps, which is literally double of the basic configuration that you see up there, and that will get you 2x the capacity. But the only thing it doesn't give you is the highest extraction efficiency, which the series configuration gives. So you can play with these things depending on what your needs are and come up with the right configuration. And the costing for each one is obviously very different. The basic configuration and the parallel configuration are literally twice 2x, and the capital cost will be 2x from that point of view. And the most expensive is the 3 vessel, 1 pump with 2x flow rate. That will be the most expensive capital configuration, but it also has the highest capacity. So we use these different configurations to define what our scale-up are and what our configurations are to get to where we want to get to. Now, the practicality is we believe that there's going to be market consolidation. So far, we have had a lot of people doing mom and pop operations with small systems. As the market grows, you will find that people with scale are going to win, because labor is one of the largest portion of the overall costing, which when we talked about in a couple slides ago, whether you have a 5-liter system or a 100-liter or a 500-liter system, you need the same amount of labor. So if you want to drive the overall costing down, you reduce labor as a percentage, and the only way to do that is by going scale. Now, this has been shown to be true for other nutraceuticals. And here are just 3 examples, whether it's fish oil or CoQ10 or astaxanthin. In all of these things, scale wins, and people end up moving from small-scale systems to large-scale systems. And we expect this to be the same even for the cannabis industry. Now, the question becomes, the next question that comes is, when you get to scale, are we better off subcontracting, or are we better off doing it ourselves? Now, that's a function of scale again. So the question, if I were to repeat the question, should everyone own their SFE, or will it be less expensive to send it out to large-scale processors? Now, in the whole food industry, especially in the cannabis, right now we do not have major regulations, because cannabis is not looked well upon by the FDA. But as soon as the regulations change, you can expect significant regulations coming down to follow CGMP requirements for the extraction. And once you say you have CGMP requirements for your product, you have a ton of quality control procedures that you need to follow. Typically, you may have 3 to 5 people dedicated to follow these CGMP requirements. And as a percentage, if you have a small operations, they become very, very expensive. It also requires you to have in-house expertise for all the different things, whether you need a mechanical engineer to maintain the equipment, a chemical engineer to run the process, or quality control people, analytical people, and especially if you want anything that says we need certification, we need CGMP certification, we need kosher certification, halal certification, organic certification. All of this requires significant amount of paperwork, which drives the cost down. I should say cost up. So what are our options? Our options are threefold, right? So you can have a co-op style for ethanol extractions of corn oil and canola oil. You can see a number of farmers joined together and they built a facility, and that facility ran their corn to extract the oil or canola to the oil. You can do the same thing, and we expect some of these to happen in the industry. The other thing we also see is people will bring in mobile units who will bring them to your facility, and they'll run it. And they will run it because they have all the expertise which comes along with the mobile units. So they'll run it, produce the oil that you want, whether it's winterized oil or refined oil, or even the unrefined oil. Any of those things, they can provide that for you. So you will have places where people will drive in a truck, 1 or 2 trailer trucks, and provide these mobile units to process at your site. And of course, the last one is you'll find people who have set up large-scale contract processing facility where you can send the material to them and they'll process it and send it back to you. And they have all the quality control people, the engineers, everything to manage it. So it, on a per kg basis, it could potentially drive the cost down. So those are the 3 options that you have besides you building it yourself and maintaining it. Now, when you go from extraction to purification, the knowledge is even more critical than extraction. Chromatographic separations require a greater technical knowledge, but the scale-up issues are similar to extraction. The regulatory issues are similar, and so we have literally the same scale-up issues that we talked about for the extraction side. What you see on the slide here is a prep scale system with 3 separators for a supercritical fluid chromatographic system. And what you see on the right is the largest DAC column for supercritical fluids built by Thar, and it's in Malaysia. They use it to separate the oils from palm oil. So if you're looking to do multiple kilograms per day, then the first question that comes is you need a large diameter column, and these columns are available all the way from 8 inches to 24 inches. And the pressure ratings on these columns have to be in the range of 175 to 300 bar. And the flow rates of CO2 and the co-solvent, typically in this case is ethanol, range as little as 5 kilos a minute to as much as 15 kilos a minute. So those are the typical specifications for a multiple kilograms per day of chromatographic product. And then the scale-up parameters are very straightforward. If you double the diameter of column, the total amount that you can process is typically 4 times. And the productivity is directly proportional to flow rate. Selectivity, which is very critical for chromatographic, is a function of particle size. Smaller the particles, you get a greater selectivity, but the cost of the particles, the chromatographic particles go up. So you need to do an optimization. typically we suggest something in the 10 to 15 micron range are probably the ideal particle size from a cost performance basis. Now, speed, capacity, and selectivity are very closely interrelated in chromatographic systems. You can get high speed, high capacity, and high selectivity. If you want all three of them, then the cost quadruples. So you have to optimize this to get the solutions that you're looking for. Lastly, I have a couple slides here which I'd like to conclude my talk and talk about what lessons we have learned today. The first one is sizing is a function of solvent to feed ratio, the capacity of the pump, the capacity of the system that you're looking for, the pump flow rate, the vessel linear velocity, and all of that. So those are all interrelated, and you start with the solvent to feed ratio and capacity to get the rest of the parameters. Subcritical extraction is very selective. It's a great way to do it, but it has a very high solvent to feed ratio and a lower efficiency. So you have to, depends on what kind of product you're looking for. And if you're looking for a winterized oil, subcritical extraction is a good way to go without going through ethanol extraction at the back end. The supercritical extraction has a much lower solvent to feed ratio, typically a factor of 5 to 10 less than the subcritical extraction. It gives you a higher extraction efficiencies because you're running at higher temperatures and pressure, but it extracts waxes and other unwanted products. So what you have to do is once you extract this, you have to go do a conventional winterization using ethanol, and that costs time and money. So it's a trade-off whether you want subcritical or supercritical extraction. Sometimes a hybrid solution might work. You may want to do a subcritical extraction to get a clean winterized oil, and then go back and change the pressure to a higher pressure and higher temperature, go back and extract what's left over. So overall you get a higher efficiency and you get two products. One is a winterized oil directly. The other one is where you have to do an ethanol extraction and produce a winterized oil. And quite a few people will take both these oils and mix them together to get a complete full spectrum oil. So those are the things. In this, I'm going to summarize by saying we do expect consolidation to happen. We expect as the market grows, you have larger and larger people coming into play, both internal for their own needs and also external for working with other people. So large-scale extraction will be the norm as we go in the future. Many groups will either set up their own wherever they think they have the technical capability and the money to do it, so they don't have to send the material. But that does not work for everybody. We'll have mobile extraction units, which will come to your facility to do this high technology extraction as a service at your site. Or you can go to a toll processor who will provide you the same service at their facility. So you have all of these options, and you can expect every one of them to be a solution for what you're trying to do. And depending on what you would like to get at the end of it, you can pick one or the other. Of course, if you have the money, the best is to set up your own large-scale extraction unit, because you can control everything. You can control what you're trying to extract, the technology, and it's all internal. But that might not work for everybody. In that case, you might be better off going to an outside facility. Or the last one is, as I mentioned earlier, a group of people can join together, create a co-op, and run the co-op for all their shareholders. So all these options are available. And with that, I would like to conclude and say Thar Process will be happy to be an extraction and purification partner. And if you have any questions please feel free to let me know and I'll be happy to answer. Thank you very much for listening to me today.
Thank you, Dr. Chordia, for that informative presentation. We will now start the live Q&A portion of this webinar. If you have any questions you'd like to ask, please do so now. Just click on that Ask a Question drop-down box located on the far left of your presentation window. Type the question into the box that appears on the screen and click the Send button. We'll answer as many questions as we have time for. So let's take a look at our incoming questions from our audience. Our first question, Dr. Chordia, is at what point is it better to subcontract instead of purchasing the extraction?
So I would say it's really a trade-off between capital investment and subcontract costing. Setting up a facility, especially a large one, requires a lot of handling and people. All of these cost money and time. It's always cheaper, especially in the short term, to subcontract the extraction and the purification. This gives you the ability to go to different vendors. And when your volume gets very large, then you can think about setting up your own facility, because by this time, you have learned the business, you're making money, and you have the time and money to invest in your own facility, optimizing to the products that you want.
Thank you, Dr. Chordia. And this next question from an audience member is a two-part question. Is supercritical CO2 extraction process too complicated? And do I need highly technical people to handle that?
Yes and no. The process is fairly simple, but because it is high pressure, it requires the use of properly designed products and caution when you're using them. In other words, if you have nuts and bolts tightening, you have to tighten them. So you really have to take care to do this properly. You cannot be whimsical about it. You can also tinker the process based on the raw material, and that requires technical understanding of what you're trying to do. So is it complicated? Yes, it's a little bit complicated. But if you have the right people, you can handle it.
Thank you. And I want to remind our audience members that any questions not answered today will be answered via email. Our next question is there any use for the leftover to raffinate?
I think that's a very good question. There is many ways to figure this out. The simplest one is you dispose it off, or you burn it, and you can take the heat that's generated to produce hot water or electricity. So that's thermal energy that you can get from your raw material. But a more interesting thing is because the cannabis plant is a high fibrous plant, and it's been used for years in textiles and ropes, it becomes a great substitute for paper or thin textiles. So you can find these upcoming new applications for the leftover material, which if you were to set up a plant to do it, it just makes more economic sense and it gets a faster return of investment.
Thank you for that. And before we close, Dr. Chordia, do you want to provide the audience with any closing remarks?
I just want to say that supercritical CO2 is a great tool. As I mentioned earlier, you cannot get a better solvent. It's physiologically compatible. It's inexpensive. If you know how to handle it, you should use it. You can use it efficiently. You can be very selective. It just makes the whole process go easy, and you're not polluting the environment.
Thank you again, Dr. Chordia, for your presentation and your important research. I'd also like to thank LabRoots for making today's educational webcast possible. Before I go, I want to remind everyone that today's webcast will be available for on-demand viewing through June 2018. You'll get an email from LabRoots letting you know that this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now, and thanks for joining us. We hope to see you again soon. Bye-bye.
Thank you all.